All right, can people see my shared screen of the agenda?
Yes.
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 Okay, great. So I think we are about to start for today's presentations. So as a reminder, each group has 7 minutes plus 3 minutes Q&A. So I will time the presentation, and I will either text or orally remind you if you're running out of time. All right. So so if no further business, sorry, someone's want to join. So I will stop sharing my screen and I will ask the speakers to share your slides with us, and okay, and so that we know which slides you're on. All right, so I think we can start. So the first group is Mr. Wong Hao-Chen and Xie Mingru. So could one of you share the screen and start your presentation?
Okay, I'm Wang Haochen, and can you hear me?
Yes, great.
Okay, so I'll share my screen now. So can you see the PowerPoint?
Yes, I can.
Okay. So
I think you should start.
okay, so we are the first group, and my name is Wang Haochen, and my teammates is Xie Mingru. And we are going to talk about this 2D icing model, and we'll use machine learning to assist the identification of face. So I'll do the first part of the presentation. And this is our outline. So first, we are going to introduce this 2D icing model. And also, we are going to introduce a simulation method called Monte Carlo method. And through this kind of a Monte Carlo method, we can kind of get the data we need to find out the phases of these spin configurations and do the machine learning. So after that, we'll talk about the data that we'll use in the machine learning. And also, this kind of a 2D icing model has some physical interpretations within this configuration. So we talk about some physical quantities that we can derive from these spin configurations. Also, and we'll do the machine learning proposals and some feature explorations. Also, the models that we'll use to do the machine learning. So the first part is that I want to introduce this 2D icing model to you. So in condensed matter, people kind of study this kind of a magnetic dipoles of atoms in materials with this icing model. And here we'll focus on 2D. So in terms of 2D, we can show in the PowerPoint here, this is a 1D icing model with spins that is aligned on a line. And 2D icing model, we have the spins on a plane. And this is a 3D icing model. So what we're interested is that we have some phases of these kind of a spin configurations. For example, the paramagnetic phase and ferromagnetic phase. So in deciding which kind of a phase these kind of a spin configurations are in, we are focusing on this maximization of entropy and minimization of energy. So as long as we know here, for 2D icing model, there's an exact solution deciding at which temperature the material is in paramagnetic phase or in ferromagnetic phase. So here is a video that gives a picture of this, these phases. So here, the video is from high temperature to low temperature. And we can see that the spins goes from disordered to ordered configurations. And here's some math. The Icing model has the Hamiltonian, or the energy, decided from this equation. And here we focus on the first part of this equation. And to calculate some physical quantity, we use this probability. And this probability gives us the expectation value of this physical quantity. Also, here I show the entropy of these spin configurations. Okay, so the next thing is that Monte Carlo simulation. So Monte Carlo simulation allow us to give more samples of these spin configurations when we want to calculate the expectation values of some physical quantities. So the spirit of this Monte Carlo simulation is that we start from a random configuration and sequentially we update each spin on each side. So whether we should update, that is, we should flip the spin at some point, is we decide the difference of the energy. If the difference of the energy is smaller than 0, and we flip the spin. If the difference is larger than 0, we flip the spin with the probability of this equation. So this is the Boltzmann distribution equation. So after this, we can get a configuration of these spins. And through many samples of these spins, we can get like more samples of this configuration and calculate the physical quantities.
Housen, just to remind you, you have 2 minutes left.
Okay, I will give the rest of the time to my partner. So maybe he can show the PowerPoint now. I don't know if he's online. Yes.
Okay, can everyone hear me?
Yes, I can hear you. Please go ahead.
Okay. Next, we will talk about the data description. And there are 3 parts in our data. First is spin configuration. They contain 110 times 10 configuration in 1001 kinds of temperature. Here. Second is temperature. The temperature is from 0 to 5, and the common difference is 0.005, and the critical temperature is at 2.38. Last is the label, which means the 2 phases of the data, the paramagnetic and ferromagnetic. And this picture shows the relation between temperature and the phase. Next, we will talk about the feature exploration. We will use spin configuration and Hamiltonian to calculate the energy, magnetization, heat capacity, and susceptibility, and treat them as high-level features. And the heat capacity are the derivative of energy, and the susceptibility is the derivative of magnetization. Last, we'll talk about our proposal of machine learning study. First, we will use DNN or DNN to train the spin configuration Hamiltonian or both of them. Second, we will use DNN or LDA model to train the high-level features. And finally, we will compare the results of two of them, and see which one is the better methods to train this data and identification the phase. And here are the reference of our study. Thank you.
Thanks. And also thanks for staying on time. So we have a couple more minutes for questions. Anyone has a question or comment for the group?
Could you explain a bit more about the entropy definition formula?
Okay. So, okay. Amiru, can you help me go to that page? So the entropy I list here is just calculated directly from the spin configuration. So this n is the total number of spin, and this plus and minus is the quantity of spins that is for spin up and spin down. So in this icing model, we want to maximize the entropy. So it kind of go into randomly organized. And the other way is that we want to minimize the energy. So these two compete with each other. So is that clear for you?
So Hamiltonian and can compute the total energy of the system, right? And
Yeah,
as here,
yes.
you can compute the total entropy of the system.
Yes.
They can be the high-level feature.
Yes. Also, we can calculate these things. So yes.
But then one thing okay, so the energy would be the Hamiltonian for each of the two-dimensional cell, two-dimensional spinner.
Yes,
And so you can get the low-level feature, the Hamiltonian of each of the spinner.
yes.
And if you sum up all, then you get a range. Okay.
Yes.
But the entropy can only be defined as the high-level feature. There's no such a definition of individual entropy of a spinner, sum up all of them.
Yes. Something kind of like that is called the correlation between the spins, but it have not been considered in this PowerPoint. So, yes.
All right, thanks. So
But sorry, I'm
sorry.
but why entropy is not one of the high-level feature for study?
We will also study this, but it's not kind of include it in this PowerPoint because I think there is already enough information in this PowerPoint.
I still don't know. So will that be part of your study, or you think that's not necessary for
We
your
can
study?
we can try to study this, but we don't know if it will be good or not. We haven't tried it yet. We can try it.
But as you said that the two-phase actually depends on the mean relation of entropy energy, right? It seems like these are two nature high-level features. Am I wrong?
Sorry, I can't hear your sound clearly.
So you define the two-phase using
Yes.
energy and entropy.
Yes.
But then why don't you just use these two as a high-level feature?
So what you're asking is that we define the phases with the Hamiltonian, or in fact, we have in our data we have three data. One is the spin configuration, and the second data is temperature, and the third data is a label, which tells us at some specific temperature if this spin configurations is in the first phase or second phase. So we kind of trained with the label of these phase information.
Okay, so just be sure we are talking about we communicate to each other. So if you go back to your previous page, you define what is two-phase, right?
Yes.
One is maximization of entropy, the other is minimization of energy. So then it looks to me, it makes sense if you should use entropy as one of your high-level feature for the study, right?
Yes, we can try it. Yes.
But why is not part of your original plan? I'm just curious.
In fact, we haven't considered the entropy because we just found that it can also be considered in this model. So we will add it into our consideration.
All right, thank you.
All right, I think we
Okay.
can move on.
Thank you.
Thanks. I think we can move on to the next group's presentation from Mr. Xiao Keyan and Ms. Shen Yunzhen. So I guess one of you is about to share your screen. And once you're ready, you can go ahead.
Okay, can everyone hear me?
Yes, I can hear you.
Okay.
But we haven't seen your slides yet.
Wait for me. Wait for me.
Yeah.
Okay, can everyone see my screen?
Yes, I can see your screen now. Great.
Okay, then, okay, let me start. And hello everyone, we are group 2 and I'm Shen Yunzhen. The other speaker is Xiao Keyan. We are talking about our Higgs production work and our preliminary report. And this is our outline today. And first of all, I will introduce the physics behind the data. Then Higgs bosons are produced from 4 production modes, including gluon-gluon fusion and vector boson fusion, and a production with a vector boson and a production with a top quark pair. And among these modes, we are interested in gluon-gluon fusion mode. From its Feynman diagram, we can see a triangle in the middle of the process. We can infer that there might be the new physics beyond the standard model here. So take a look at these 4 Feynman diagrams. All of them have the process of Higgs decay into 2 big quarks, which is so-called leading double B-tech jet. If we want to distinguish them, we can focus on the non-Higgs leading jet, which we draw orange circle on. Based on the different properties like momentum or mass, we can classify each data easily. Therefore, what we want to do in this study is to identify the production modes accurately by the machine learning. And based on the previous work, there are 3 kinds of data. The first one is high-level features, and the second one is data constituent, and the third one is data project X. And we found out all of their structures and features. Here is the high-level features data frame. There are the columns which telling us the 4 different production modes. And for the second data frame, the last column label tells us the production mode it belongs to. And for the last kind of data, it contains lots of MPC files, and the data was classified either. Okay, and after doing some visualizations, we observed high-level features are much more suitable for training by DNA model. And take some features histograms, for example, and like Higgs PT, non-Higgs leading PT, and non-Higgs leading mass. At first, we suppose that only those 3 features are good for us doing training data. But while we plot each of the scattering plots, we observe that if we only take the 3 features, the scatter plots show us the classification might be difficult. Therefore, we think training more features is the better way. And for the last kind of the data, we reconstruct events and plot the jet images with different modes in three channels, just like these three. And yes, according to the image, we observe they are in slightly different. Therefore, we think we can apply CNN model or other image training ways to distinguish the production modes. And the next page, I will give Xiaoke Yang.
Hello?
Should I share my screen?
You can continue sharing your screen. I'll just...
Okay. Then the next page is
So,
okay.
as a result, we know that we can train high-level features with DNN model and low-level features with CNN model. And since we have both low and high-level features, a thought came to my mind is that maybe we can train the model and then concatenate them to get a more accuracy result by both using the high-level features and low-level features at the same time. So our proposal is, in the beginning, we first train a DN model, and then we train another CNN model, and then put it in the same, like a dense layer together, and then predict the result. This is our thought. So we have to first train DNN and CNN, and next we just Google and we check up the reference that Alan gave us. So there, for high-level features, the paper used BDT to train it, and for low-level features, they use full event image and leading non-Higgs jet to train it. We haven't reproduced their results yet. And recently, we found that so before our training, we found that autokeras is a module that can automatically create a model to train. So the next page shows. Hello. Hey, help me turn to the next page. Wait, sorry, this is our recent work. So this is the laptop is our code, and this is really extremely short to before. Sorry. In the past, we need to first assign a model, and then to train it, and then see the result and alter the model to get a better accuracy. However, in this AutoKeras module, it automatically create a model and then train it. And after training, it gets its accuracy. It inputs AutoKeras use the weight of the nodes, and then the number of weights, the number of layers, and then put it into another model, and then train it with the accuracy. So for every trial, it
Koyan, your group is out of time, so try to wrap up in the next minute or so.
So every trial it create a model and then train. However, our recent result is not good enough. That's because I think the model is AutoKeras is not able to create a suitable model yet. And I think we'll first try to reproduce BDT and see if there is any preprocessing we can do. And that's all.
Thanks. Any questions or comments for group 2?
Thanks. I think this is a quite advanced talk, which go beyond what we request for presentation today. And I highly encourage everyone pay attention on what's the required materials to present in this meeting. Then we can stay in time.
I thought we start at 10:29.
The point is not about the time, actually. The point is about what's the required material to present in this meeting.
Sure.
All right. Any other questions or comments?
Okay, can I ask some questions?
Yes.
Yeah. Because at the previous page you talk about you use CNN combined DNN. I heard that there's another method that maybe you can add your raw data to the after few layers of CNN, and this may preserve the features you may lose in the first CNN model. Like so I heard there's a way that you put your raw data back to like after few layers after. So maybe you can try this to get better results. So
Okay, thank you.
All right. Given the interest of time, I think we can move on to the next group. So group 3. So group 3 is Mr. Sun Ruidi and Mr. Wang Chunyi. So one of you please go ahead and share your screen.
Good morning, everyone. We are Group 3, and our topic is charge particle tracking. First, we will talk about how the data is collected in the CMS tracker. So here we can see how when the charge particle is traveling across the tracker, it will generate a signal in each layer. This signal is generated by the energy transfer by the heat of the charged particle. So it will generate an electron, and this electron will be read out by the circuitry underneath the silicon detector. So this way, we are able to have a signature in each layer from each particle. So then the task comes to the generation of each of the points of each layer that was given by the particle. So here we can see how the signal is generated when the charged particle goes across the sensor pixel. The dimension is quite small, it's 150 micrometers. So each pixel has its own readout chip. So we, in this way, we have enough precision to measure the position where the charged particle has traveled across each layer. So in this way, we generate the data, and then we can collect pairs of events in each layer. So for example, in this region, we have a pair of events. We have a point generated in this layer, in this one, and we can regenerate the path that the charged particle took. And then we can reconstruct all the trajectory that the charged particle left. And then we also, in the data and the features, we also have the momentum. So we are able to construct especially reconstruct all the trajectory, and then we can use the momentum to distinguish which particle we are working on, because we remember that in this experiment, these charged particles are traveling in a magnetic field. So the trajectory will be curved depending on how massive is the particle. So in the data set we can see that we have a lot of events. For example, we see that the number of pairs per particle is quite huge, because we are talking about only 4 layers. We are working on the volume 8. And also we can see the particles that are crossing each barrel. For example, we can see that some of them are just crossing the first layer, others are crossing all the 4 layers, and we can also know which particles are traveling in which barrel. So we are using this the data set that we have it at hand to reconstruct the trajectories. And because we have also, we can say we have false trajectories, because the data we get is the heat in each layer. So then we can reconstruct false trajectories that we don't need, but at the same time we can use them to compare how good is our model. So at the end we will construct the true trajectories in the trajectories of each particle, and then we will use them, as my teammate Ian will talk about how we will use these particles and this data to construct our model.
Okay. Does anyone can see my slides?
Yes.
Okay. Now let's start to see our data localized. Our data is localized. This is a series of hits, and we can virtualize into a 3D plot, and it has the layer structure of the data. So what is the assumption and relations behind this data? When a particle passing through a detector, a series of hits will be recorded, and we want to seek the relation to reconnect those hits. So first, the absolute position of the hit is not very useful, and the important thing is the relative position between the hits of each layer. So we can connect the two hits. Two hits can be created by the same particle only when they satisfy certain condition. And we connect all those pairs of the hits which is satisfy those conditions. And with those connection and hits, we can create a graph structure. So how we have the graph, and how do we deal with those graph? And first, our goal is to identify the true trajectory by connecting the correct hit. So we translate into the graph language, and we create a function apply on every edge and node. So we can get a score for each edge and use this score to remove the false connections. So,
Chen, just to remind you, you have about 1 minute.
Okay, how do we do this? Graph structure. This can be done with the GNN. So a GNN has the many approaches. That is the one approach. It separates the graph network into the node network and edge network. With one is to update the node and a node score, and another update the edge score. So so with these two blocks, we can build our network with a messenger passing network with a series of non-network, or just or added some other mechanism to build edge nodes. That's so-called attention messenger passing, and
we can use the other techniques such as recursion network to strengthen our model, or use the residual net technique to to deal with the gradient vanish problem. So this in the literature, this one is to be claimed has the best performance, and we will follow this route to complete our project and seek some improvement. Then this is our reference, and thank you for listening.
Thanks. So we have a couple minutes for questions and answer. So any questions or comments for this group?
So I like this talk, and it really have a clear presentation about what you plan to do, but also you reveal this is going to be a quite challenging project. Yeah. So can you comment on what, in your point of view, what's going to be the most challenging part to carry out this project?
There's a lot of the pre-process for the data. So in my presentation, I just say it should be we connect all the pair of hit with the certain condition, but this condition is actually very complicated process. So, and in the literature, it actually trained another model to do this connection, and I think there is a very important preprocessing for our GNN to clear all the data and make the prediction. Also, we also find out that the connection is very large, because the vertex is very large, and the connection is must be done in a quite long time. So we plan to use some multi-threading or multi-GPU method to solve it, and that's what I think so far. And we haven't actually trained the GNN, so the performance of the GNN is still unknown for us. Yes, so far.
Okay, so you mentioned you might hit the hardware limitation to train this model. And can you confirm what kind of computing system you are using for this project?
I just use my laptop so far, so it's not very we haven't put it on the large computer, so yes. And
we are just using the GPUs from Carlo.
Sorry, I cannot understand you. What did you say?
That we are just using the GPUs from Carlo, and that's it. We don't have more resources to compute.
Yeah, so we do claim a few a GPU from Academic Sinica. Are you planning to use that?
We haven't tried this. And if needed, we will try it.
Got it. Okay, thank you.
All right, thanks. So I think we can move on to group 4 from Mr. Wang Chen and Mr. Lin Zhongwen. So I guess one of you can share your screen. And I think Chen Yi, you can stop sharing.
Okay.
Well, can anyone hear me?
Yes, but could you remind me who you are? I cannot tell you from your shared your.
Oh, my name is Zhongwen.
Okay, Zhongwen. Okay, I can hear you. You are going to share your screen?
Well, yeah, some problem.
Or you want to use my screen?
Okay, I use your screen. Okay.
Can everyone see my screen?
Yes, I can see your screen.
Okay, so
Okay.
in Zhongwen will first presentation.
Okay, go ahead.
Okay. My name is Lin Zhongwen, and our topic is top jets, and my teammate is Wang Chen. And then first we're talking about data description. We're just talking about the shape of the data, and we get and we find every file we get the data we get, there are high level feature and low level feature, and every jet they are labeled with each jet, and then we found that the amount of jets is there are a lot jets like we show on the PPT, and high level feature there are 16 feature, and there are jet mass, multiplicity, and delog, and energy correlation function. And energy correlation function, there are 13 different feature, and we found the formula, and we find we don't know what happened. So so we just actually know there are about energy, the feature about energy and the mass. Yeah, actually mass, and then there are low for low feature, and mainly we think it's used to use the high level features to train the DNA model. And next page, and then we will talk about this physics behind the data. And first we introduce the top quark, and there are simple sense knowledge for top quark. And top quark is the most massive fundamental particles, and the charge is 2 divided by 3, and the mass is 172 electron volts divided by light speed of light square. And then the mean lifetime of the top quark is 5 times 10 minus 10 minus 10 的负25次方 time seconds, and because the top quark it decays very soon, so it's last quark we find in these 6 known fundamental particles, and then is this Feynman diagram, and there's another thing said before, and this is the most we found in the most we found is T channel and and then that's it.
You have about 2 minutes, so beware for your time.
Okay, and then let my teammate to introduce the next page.
Okay, so I'm Wang Chen, and now I'm introduce the feature exploration and our model plane. So from this paper, we picked out 16 observables to train our DNA model. So yes, it is introduced before. And one thing I want to mention is that I think JD2B1 and JD2A1B1 is the same. So because our observables we picked is coming from this paper, so I maybe if the DNA model are trained not well, we will change these two feature, one of these two feature, and also we make a correlation table to these 16 features. So as I mentioned before, these two features, I think it is the same, but I don't know why. And as you can see, the most of these features are not quite correlated. So I think these 16 features will be well to train our DNA model. So and also we plot out the total figure to each jet, to each labeled jet. So this is gluon jet, this is quark jet, and WZ boson jet, and this is what we found is what we want to find is top jet. So we can we from this paper we will first decide a DNA model like this structure to train our model, DNA model, and maybe if we have time or the DNA model is not well, we will take into CM model from this paper. But actually, we found a little bit problem to the CM model. Yeah, but if the DNA model is not quite well, we'll use CM model, or maybe we can do both, then compare them. Yes, so that's our reference. Okay, does anyone have question?
Yeah, thanks. Any question or comments?
Can you comment on what's the model you try to work on in terms of is a binary classifier or a multi-classifier?
I think it's multi-classifier. We want to classify into these five. These five label. Like is gluon jet, quark jet,
Okay, so it's a five classifier, not just five.
Okay.
Okay.
Yes.
Because I'm confused by when you say you just want to identify top, but you actually want to identify all the five, right?
Oh yeah, I maybe speak wrong. So
And
any
it's
other
very
question?
interesting that you point out D2B1 and D2A1B1 seems identical. Can you figure out the mathematical formula to understand how these variables are defined? Then maybe you can comment on, and they are actually redundant. This would be
Yes,
great. Figure it out.
actually, we try to learn what is energy correlation function in this paper, but we haven't learned well. So yes.
But so you have 3 weeks to figure it out. So
Yes,
that's nice. Yeah, very good.
But can you see, at least check from the correlation function that these two features are, say, 100% correlated? Because you see a correlation plot, and I remember you heard you say it's all independent or something like that. Maybe I misheard you.
Yes, this is JD2A1B1. So if you look like this, the diagonal term is 1. That is
okay.
Because, yes.
Indeed, we look 100% correlated.
Yeah, we can see here.
Okay.
This one is 1. Yes.
Okay, thanks.
So any other question?
All right. If no other question or comments, and I think we can move on to the last presentation for today, Mr. Chen Shinkong and Ms. Wang Yuhui. So, so one of you, please go ahead and share your slide.
Yes. Can everyone see my screen?
Yes.
Okay.
Please go ahead.
Okay. My teammate. Okay. We are the group 5, and I'm Chen Xinhong. My groupmate is Wang Yuhui. And here's hello, my teammate.
I can hear you and also see your slide. I think you can continue.
But this part is my teammate.
Oh,
yeah.
You're supposed to hand down to Yuhui.
Yeah.
Can everybody hear me? I
Yes.
missed the meeting. And so first is my part. First, I want to introduce you the physics behind this data set. And first is what is co-collapse supernovae, and second is what is gravitational wave, and final is the rotating core collapse. So the next page. And first is the properties to the core collapse supernovae. At the end of the ages of the star, it will become a layer shares of the nuclear fusion. So the nuclear fusion provides our pressure against the gravity and stabilize the stellar structure. But since the iron core, the inside the iron core and the nickel have the highest binding energy cannot be produced at the core by fusion. So the core is supported only by the degeneracy pressure of electrons. But when the core mass is compressed, when the core mass reaches the limit, Chandrasekhar limit, the degeneracy pressure of electron is not enough to resist the gravitational pressure, so it starts to collapse like figure B. And the inner part of the core is compressed into the neutrons, like figure C. But the infalling materials will be bounced and form an outward propagating shock phone like D. But the shock phone energy is not big enough. It's not strong enough to become a supernova explosion to destroy all the stars. The shock was dosed. And it is believed that after the neutrino interaction and some mechanics, the shock wave continue propagates outward and star explodes. So this is its process. So next page. So the problem is the mechanism of this process still remain unclear because of the restriction of observation on core collapse supernovae, because we can only detect photons after the shock breakout. So the inner physics and the short time effect of the supernovae is hard to understand. So how to how can we understand the inner physics of the core class supernovae? It's detecting the gravitational waves from the early stage of the inner core collapse. So next page, I will because the gravitational waves are disturbance in the curvature of space-time and generated by the accelerated masses and the masses quadrilateral momentum. So when the core collapse, the gravitational wave has propagated. So if we can detect the gravitational wave, we can know the early stage of the core collapse. So astrophysics attempts to simulate models of the gravitational wave by some constraints of the feature of the core class supernovae. So if we can, next page. If we can,
Sure.
no, upper.
Just remind you, you have 3 minutes left.
Okay. So if we can fit the model, we can know the theoretical physics. Okay, next page. So this is the gravitational wave waveform. So my partner will introduce this part. So I want to and this is our data set we just showed you. And I want to say is the rotating core. Okay, so next page. Hello. Okay,
Yes.
so in this page, the left one, we can know the rotational. This is the quadrilateral momentum. We can know the left part is the smaller rotation and the right part is the upper rotation. So we can know the rotation has a significant effect on the quadrilateral momentum and influence the gravitational wave. Okay, so I give to my partner.
Okay, here I continue to do the data exploration. So this is the data set for Zenodo, and it includes some no collapse and EOS equations that we would use. After filter is left about 1,700 data, and it's divided into 3 groups. And this one I skip this because it will not use. And waveform is the 4 quantities and times stored in this group. The quantity are in time sequence, and what we need is what is the time after co-bounce, and one is the strength time distance. All the simulation, the distance are given as a constant 10 kilo per second. And here it show the waveform for 6 EOS. So we will select the signal before TB plus 6 minus 6 ms to exclude the effect of convection here. Okay, what is reduced data? Reduced data, it has 26 quantity stored, but we only need 3. This is omega 0, the initial rotation rate, and this is T bounce, and the T bounce, and these 2 represents the starting times and ending times of the core bond. This is the all quantity histogram, and for us, we will only focus on the rotational effect. We plot only the rotational distribution. We have five differential rotations, and each of these has some profile as shown here.
Shinkong, you guys are running out of time, so try to wrap up in the next minute or so.
Oh, okay. Oh, the next one is just show the to have some intuition of what the omega 0 affects the waveform. So our proposal is to train a model that can extract the rotational effect. That is the initial rotation rate from the waveform, and here's our presentation. Here's the reference. Thank you for listening.
All right, thanks. Any questions or comments?
Thank you for the talk. I think this is the most challenging talk I hear today. I really like the way you introduced the introduction about the physics in the very beginning. That I know, but I just failed catching up the presentation since page 4, after page 6.
Page 6. Sorry.
Starting from page 6,
Yeah.
I basically cannot understand almost every single slide.
Sorry.
Maybe
because, okay.
I think there are several technical detail, and so I understand the challenge here. But now maybe I can just clarify a few things. You show several plots. Can you comment on which plot is made by you?
Oh, sorry. The before 7 is
just point out which slide are the plots made by you. I just want to say.
After page 7.
Yeah, after page
7
is made by you.
Yeah. This plot is
okay. This is
the
sorry page. Can you do it one by one? Which page of slide are made by you?
After 7 is all made by us.
The page 9 is made by you?
Yes.
And page 10 is also made by you?
Yes.
From the
okay.
data.
And then page 12 and page 13 and also page 14 is made by you?
Yes.
Okay. Interesting. So now, if I understand correct, you want to do a parameter estimate. You want to estimate omega 0. Is that right?
Yes.
Okay. And is that true? Page 14 is an related function. It's a function form.
It's not an analytic function. It's
and you want to fit the data. So data, which one is a function?
So actually, this is not the function because we cannot straightforwardly know the rotation rate from the function. So we can see the page 6. Can you go to the page 6? The page 6, the H plus is the strength of the gravitational wave. So it's influenced by the mass quadrilateral momentum. But the rotation and the A and the equation of state will influence the quadrilateral momentum. I'm sorry, I have no time to explain more of the equation of state. So it's it requires some process in between the density, temperature, and some kind. So it's very important to influence the mechanics inside the core.
Maybe let me clarify a few things. So you download some simulation data from outside, right?
Yes.
And which page of slide are the plots made using those data?
Using those data is behind 7. So my PowerPoint to the our PowerPoint to the 7 is on the paper.
Yeah, even page 14. Can you go to page 14?
Yes.
This plot can all be made using those download data?
Yes.
Yes. I can show.
So the data. Okay, I think.
Yeah, it's here.
Okay, I see. But then, what exactly you want to do? And can you try again? Because I don't understand what's the goal of this study?
So the goal of the study is that if we can training a model to determine the waveforms, just like if we just pretend this is the real waveform of the gravitational wave when we detect. So
okay.
when we detect this, then we can put it in the training model and to know the exact rotation rate, because we cannot straightforwardly to know the rotation rate from that plot from the slide 14, because this the H plus is influenced by many features, and it's just the total.
So page 14 is just the waveform for one single omega 0.
No, it's many omega 0. We can see the
right, exactly. So each curve represents different omega 0, right?
Yes. Yes.
Okay. So then you want to train the model, can determine if I give you a waveform, you want to determine what's omega 0 of this waveform. Is that right?
And this part, yes, and this part is only the equation of state to the certain one, and the A is also the certain one. So it will have many kind of features. So it will have the different waveforms actually with different features. So it's not easy to see the rotational and straightforward. Yeah.
So how do you want to construct the model architecture to solve this problem?
Can you say that again?
How do you want to construct a neural network model to solve this problem?
Now we are thinking about maybe the RNN model to do this part. But we still have not discussed so much about that. So we are going to do that after. Sorry.
Okay. So I'm working with林峰利老师 in Shida, okay, in some gravitational wave project. So he recently just sent one of their gravitational wave parameter estimate model to us. And he agreed that their model can just share with student, work with the team. So I can forward their model to you. You can take a look because in their purpose, they are just interested to do the parameter estimate of binary black hole system. Yeah. And in your case, you want to do the parameter estimate of omega 0 and A, right?
Yeah, but
so,
the difference is our gravitational wave is from the quark-like supernovae.
Yeah. But the key point is the idea of fitting the strength versus the time data.
Yes.
And it's the same. Yeah. It's just the physics are different, right?
Yeah. Yes.
But I think that the similar architecture can be tested. Yeah.
Yes. Yes.
But do you also need to do a typical Fourier transform analysis, or you just need to study the strength versus time waveform?
I think maybe.
Because the typical gravitational wave study, you need to do the noise, right? And you need to figure out different noise background. And or this is not part of your concern. You just want to have assuming there's no background, and then you have a signal only, and you want to just do the PE of the signal parameter.
Yes.
Because the model they have is trying to analyze the real data, so they need to do the denoise process.
Yes. Yes. But I think the paper of the data set is not mentioned this part, so maybe we need to check the.
Okay, so I see. For you, you are not worried about noise. You really now you just have a pure signal, assuming noise can be subtracted out, and you want to study the difference of the model due to the parameter variations, and then you want to see what's the rest of the.
So
okay.
Yes.
Okay. Yeah. Good.
So there are another questions or so thank you everyone.
Thanks. So I think we're done for today. I don't know if Shijie, you want to anything you want to announce or?
Oh, I have one comment, and I think the Higgs production project and the top taking project both have high-level feature data and low-level feature data. Both are multi-classifier problems. And in the Higgs production talk today, and there's a idea about how to combine high-level feature and low-level feature together to maybe get a better model. So this kind of idea actually could also be interesting for people who do the top tagging. And I encourage you the two groups should have some discussion with each other, and some idea can possibly share with each other. It would be nice.
Okay.
Yeah. Thanks for the suggestion, Shijie. I think that's very nice. So thanks for all the speakers, all the groups for today, and I think we can close this Google Meet meeting room, and I think the TAs will remain online for another hour so that you can contact TA via Discord for your final projects. So thanks everyone. I think I can close the meeting. Goodbye.
So sorry. So to be sure.
Okay. Sorry.
So, and David and Aiden are still online?
I'm still online, yes.
No, David and Aiden, are both of you still online?
Right, yes. Can you hear me?
Okay, great. So do you want to comment on how do we want to sign off today, and what do we want to see from each of the group? David, Aiden, can you comment?
Yeah. I remember that we didn't need people assign any. If people can prepare a few slides to summarize what they did today.
I don't think I can hear Aiden. If someone can understand Aiden, could you repeat Aiden's comment?
So I think Alan said, I think for this week, we just asked each group to give us a short summary about their current progress. And Alan, you said made a few slides. I think they can either make a few slides or just write a Kaggle notebook and share with us. I think that's what we said last time. We discussed last time. Could you confirm?
So I'm confused. Does each group need to prepare just maybe 1 or 2 pages slide, or they need to share the notebook so we can see everyone's progress?
I think they can do either way, but I think maybe just all have. I think just.
No, I don't think this is confusing. We need a consistent plan, right?
Right, I'm just about to say. I think it's probably easier that we just use Kaggle notebooks. I think that's easier for us to track. So I think each group can share with us a Kaggle notebook, and I think just a few words or a few plots summarizing your current progress, and maybe and also like some outlook of what you plan to do, say, next week. So what you have done up to now for your final project, and what you plan to do next in order to complete the final project. I think that's all we require for signing off for today.
Okay.
And Alan,
to me, it's a very
yes.
To me, it's a very clear request. Yeah, is it clear to everyone that to sign off today, you need a Kaggle notebook and share with TA and show your progress and with a brief statement about your plan and what you plan to continue next week? Is that clear to everyone?
So in the next week, we still need to make slides to present our report.
Next week, there will be another 5 groups to give a preliminary report.
Okay. Yes. So today we need to use Kaggle to show our current state.
Exactly.
Okay. Sure.
Yeah, so in each your notebook, in the last cell, you need to use markdown to summaries
what you did today. And if you have some plot, you also can put in the cell behind this summary cell. It's clear.
Yeah, it's the same like it's one notebook per group. Yeah.
Yes. Yes.
All right. Thanks for the reminder, Shijie. And just repeat. So each group, please share with us a Cargo notebook to briefly summarize your current status and or maybe also a few words on your plan to finalize your project. And that's for signing off for today. So meaning you have to do that by 1 p.m. today. All right. So if no other business or announcement, I think we'll go ahead and close the meeting. So thanks, everyone.
Thank you.
Bye.
We hope today. Bye-bye.